In this video, we're going to be talking a little bit about radiometric dating. So that is the process by which anthropologists and archaeologists and those sorts of researchers actually determine the age of the artifacts and specimens that they're studying. So this is very much an application of what we learned in the previous video, because we're using that kinetics of radioactive decay and our understanding of how these types of reactions happen to actually determine how much time has passed since something was created or since a creature died. So what we're doing is really using the relative abundance of radioactive isotopes to estimate the age of a sample. So we know that different elements have different isotopes. So atoms with different numbers of neutrons that have different masses are known as isotopes, and many elements have several isotopes that are naturally occurring, that occur in nature, but they don't all occur like in equal amounts. They have different, what we call natural abundances, and what is normal for different elements is pretty well established. So the typical natural abundance of isotopes is well established. So if a certain percentage of the world's carbon typically exists as carbon-14, for example, we can compare how much carbon-14 is in a sample now to get an idea of when it was created and compare that to how much typically would be in that substance to get an understanding of the age of a sample. So we can compare the actual abundance of an isotope in a sample with its typical natural abundance, is essentially what we're doing. In this process. So probably the most well-known type of radiometric dating is often referred to as carbon dating. And this measures the amount of carbon-14 in your sample. And carbon-14 has a half-life of 5,730 years. It's great for determining the age of organisms. Because, as you know, living things contain lots of carbon. So that makes them easier to study by this method, because only a small percentage of the carbon in the world exists as carbon-14. So if there's very little carbon in whatever sample you're trying to analyze to begin with, then there's very, very, very little carbon-14, even when it's brand new. So this is also commonly used for early human artifacts. And it generally works well for any samples up to about 60,000 years old or so. anything older than that is going to have too little carbon-14 remaining to reliably detect and be able to study accurately. So to detect. So solving these types of problems is exactly like what we were doing yesterday, except we are generally solving for t, solving for the time, for how much time has passed since something was created. So we can look at how old is an artifact that contains 10% of its original carbon-14. Again, that half-life is 5,730 years. So take a minute, pause here, and try this one on your own. It's using exactly the same equations that we used yesterday, just solving for t. Alrighty, so I like to kind of take inventory of what I know and what I don't. I know that the half-life is 5,730 years. I don't know K, but I can find it, and I'm going to need it, so that's going to be the first thing that I do. So my half-life is equal to 0.693 over K, which means that my half-life, sorry, my K is 0.693 over the half-life, which gets me, or 0.693 over 5,730 years, which gets me a value of K of 1.21 times 10 to the minus fourth inverse years. So then going on to the rest of my variables, t, how much time has passed since this artifact was created, is what we're looking to solve for. I'm looking to find that for an artifact that has been found to have 10% of the carbon that it once had. So we can assume we started with 100%, we started with however much was there, and we're down to 10% of however much we started with, is what we're looking at here. So at this point, I need to use my other equations. So I have minus kt is equal to the natural log of nt over n0. Since I'm solving for t, I want to use this addition of the equation. I know both nt and n0, so I can plug this whole expression into my calculator and find the answer, and or find the value of this expression rather, and then it's pretty straightforward to get t from there. So if we plug in everything that we know, K is 1.21 times 10 to the minus fourth. T is what we're solving for. And then we have natural log of 10 over 100. So if we put that log expression into a calculator, you will find that that is equal to negative 2.303-ish. And then if we divide both sides by negative K, we find a value for T in the ballpark of 19,000 years. So we can say that this artifact is approximately 19,000 years old. So that works well within the range of carbon dating. For older objects, other isotopes with longer half-lives need to be used. So that is the only difference between carbon dating and other types of radiometric dating, is just what isotope you're actually studying. So carbon dating is pretty common. It works well for a lot of things, but it does have a limit because its half-life is long, but not incredibly long. We do have a limit of about 60,000 years old, and after that, there's going to be such a tiny fraction of the carbon-14 remaining that it's going to be hard to detect at all. So we just need to use a different isotope with a longer half-life. One of the longest ones is uranium-235, has a half-life in the millions of years area, so that works well for super old things. And there are lots of other options as well. So this was just an application of the kinetic stuff that we talked about in the previous video, and that's all.